Hello and welcome to another one of D's ADD videos. Today we're going to be looking at this example where two people are standing on an ice mountain. We're going to assume that it's a flat surface that's frictionless, connected by light rope. Anytime you hear the words light rope, that means that it's got no mass. We don't have to consider it in the sum of the forces. And then over a frictionless pulley. Basically what we're going to do is we're going to release these people from rest, and we're going to see who's going to meet their doom and who's going to get to the rope to safety. So if we look at the system, we can determine that right is positive, left is negative, up is positive, down is negative. Now, whether we're talking about up and to the right, or down and to the right, that's positive, or left and down, or left and up, that's negative. So once that's established, we can do a free body diagram for each person separately. So this person has a normal force perpendicular to the surface, a tension pulling it that way, or him or her, and a weight pulling them straight down. If you do this correctly, and align your axes properly, what I like to do is put the normal force along with the y-axis, and the direction of motion is the x-axis usually. If that is the case, then you only have one angle to deal with and one vector that you need to break down into components. So here, if you do it properly, your angle of inclination should equal to the angle between the weight vector and your y-axis. So just to prove that's true, here's your angle of inclination. This has to be 60 degrees because they all add up to 180. And then if that's 60 degrees, this has to be 30 degrees because it's a complement. To make 90 degrees, you need another 30 degrees. And this is a 90-degree angle. So now we have our W1 vector in its components. We start at the beginning, and our y component takes us here, and then the x component takes us to the arrow tip of the weight vector. And notice the weight vector is going to the left, so that means the negative x direction. Tension would be the positive x direction. We only care about the x direction here because the y acceleration would be down, gravity. So now what we can do is we can ask ourselves which trig function has the opposite vector and the hypotenuse. That would be sine. So we can use sine to determine what the x component is in terms of the weight vector. Sine is opposite over hypotenuse, and then multiply the W1. Remember, weight is equal to mass times gravity, and there is W1 in the x direction. Applying the same logic to W2, there's your free body diagram for M2, and normal force perpendicular to the surface, tension that way, weight straight down. So now I'm orienting the axis again along the two main ones to minimize my work. We want the angle between the y-axis and your weight component to be 60. So let's see if that's true. Two crossing lines, their vertices are congruent. So this is 60. So that means that this has to be 90, which means this has to be 30, which means this has to be 60. All right, so now what we can do is we can do the same thing. We can W2 vector into its components using the sine function again, and the opposite over the hypotenuse would be sine. So doing the same exact logic, you get this for W2. Newton's second law, because the system will be in motion, it's doubtful that they will cancel each other out perfectly. And when you do that, you end up with the sum of the forces in the x is equal to tension minus W1 equals mass times acceleration. So tension minus W1 equals mass times acceleration. Reason being, tension's in the positive x to the right, W1 is in the negative x direction. For the second block, we have the weight going in the positive x direction and the tension going to the left. So that would be weight positive, tension negative. Now you have a system of two unknowns with two equations. So solve for tension and acceleration as unknowns. You can either solve for tension and plug it into the other equation. I'm just going to add these two equations because the tensions cancel out nice and neat. And when you do that, you end up with this. And what you can do is at that point, you can plug in the weights from above. If you remember, we calculated what W2x equals and W1x equals. And we can also factor out the a that's common. So let's see that in action. So here's the weights plugged in, acceleration factored out. Take what you had originally, divide by what you're factoring out if you want to figure out what's left. Originally, factor out left. So now it's just algebra, divide by that, plug and chug, and when you do so, you get that here. You can check your own work. And then here, when you finish doing that, you end up with a positive acceleration, so the system will move to the right. All right, had this been negative, it'd be to the left. So who's going to pass? Well, it's actually the lighter person, opposite what common sense might indicate. You would think the heavier person would be pulled to their death, but no, it's the lighter person. It's because the angle is much steeper here. All right, so the tension, how do we find the tension? Well, we're going to have to go back, and we are going to have to plug into one of those equations. So the top one's got tension positive, so if you plug into that, you should end up with something that looks like this, and it's literally solving algebraically for tension. You know numerically everything else. So just bring it over. You can plug in your numbers and then add the numbers first if you want, probably easier than the way I did it. And then when you add these two together, you're going to end up with, what's that, 573 newtons, 0.7 newtons as your final answer. All right. So hopefully this clarified a little bit some Newton's second law thoughts that you had in your head, and also you're able to rationalize my logic here. Some of you might have wanted to use just one axis in the middle. That's fine. You can do it that way as well. Just practice, practice, practice is my advice to you, because it might seem intimidating at first, but the more you do it, you'll find out it's not as bad as you think. All right. Thanks for watching. Have a great day.